Can you hear me?
Yeah.
Yes.
Great. So today we're going to talk a bit about validation, which is, hopefully will be easier for us to understand. I'll touch also on a model selection, a kind of related, you'll see why in a minute. Hopefully these topics will be easier to understand now that we talked about the union bound talked about learning in general. So one of the things we are interested in is to determine if the machine learning model, if it's going to behave well when we make it operational, when we start to use it as part of a system. And in order to do that, we need to estimate the behavior of a random variable we are interested in. So I'll take you through an example here of how we do this. The general setting is very similar. The only difference between what I'm going to do here today and the general setting is that in general, we're not focused on only whether or not the model is equal on a certain point to the function we're trying to learn, but we have some general loss function that when there's a mistake, there's a discrepancy between the model. Here the model is h, and the function is f that we're trying to learn. When there's this discrepancy, there's going to be some general cost to that discrepancy. Just a minute. Okay, so the general setting is very simple. What we have is some function we don't know, f, we're trying to learn, and we already applied some sort of machine learning, and we got a function that will learn h, and h is not equal to f, but ideally h approximates. And what we are interested here is simply in the probability that in the future, when we deploy h and use it, the probability of making a mistake, which will be on a specific data point, saying h of x, which is different than f of x. So we're only interested in that probability. As I said, in general, you might have a different loss function. A typical different example would be fx minus hx absolute value, or the square fx minus hx. Okay? So that's the probability we're interested in here. And we basically want to estimate this probability. Just note that this probability is also an average, right? It's also the average of the variable x, which is defined as the indicator variable, 1 when it's different, and 0 otherwise. So the average of x would be 1 times this probability plus 0 times 1 minus this probability. So it's just this. So this number here, the probability is just the average of the indicator the indicator variable, which represents the average number of times in which we're going to make a mistake. And in general, instead of the average of fx not being equal to hx, we will have some general loss function here, and we would take the average on that random variable. So this is a very specific example, but actually it's the same thing with general loss function. Just there's some technical complication, and there's a question of whether the average exists, whether the standard deviation exists, whether we can bound it, bounded probability, and so on. So there's some technical other questions, but this is the general setting. So the general setting is that we want to validate f, the behavior of h compared to f, because h approximates f, and want to know the probability of f being different than h, which is represented as the average of this random variable, the indicator random variable. So that's the general setting. Any questions up to now, or is it clear? Is it clear, the setting?
Yes.
Okay, great. So the way we do this is by choosing a random sample from the data. Each of the element is x1 to xv. Each of the element we choose with the same distribution and independently, and we create a new, sometimes they call it fresh data set for the validation stage. Now, many times you'll see that the common practice is to take the data set and randomly separate it to 20%, 80% state, and then use 20% as the validation. This is equivalent to what I've just described. I mean, as long as you don't use the 20% in the learning. So a common, very severe pitfall is to use the 20% data. Sometimes it's called the holdout, 20% data that you want to use in order to understand the projection, understand how well the machine learning will do when you start using it. So that data, if you use it for learning, you're dead in the water. Then you can't project how the machine learning will perform, basically. So, okay, so I'm choosing this fresh sample. Hopefully, it's representative of the data I'll see in reality. That's the assumption. And now I want to estimate the probability of error. the probability of fx being different than hx. So a few observations that you're probably familiar with at this. So one is that what we're interested in, or what estimates the probability of this probability of error, is the average, right? So adding all of these numbers and dividing by v would give me an average, which I call y, another random variable, and that average will estimate this probability. Okay? So y is the random variable I'm trying to analyze. And the statistics y, which is the sum of 1 over v, the sum of xi, this statistics approximates this probability of error, and I want to know how well it does it, which is basically the simplest way of representing what we do in machine learning in some sense. Because what we do in machine learning is bounding errors of this sort. But this is the simple case in which we can do this. Just one model. We're done with the learning, and we're just trying to estimate the error. So if you think about the things we talked about before about pack learning and the union bound and the tail inequalities, this is just a very, very simple case in which what I call the model there is just one function h. So I don't have a lot of functions. I have just one function. Any questions up to now? Thoughts? Is it clear?
I can follow so far.
Great, great.
Yeah, me too.
Great. Excellent. Okay, so let's look at the average. What's the average of y? The average of y, well, average is a linear functional, so you get that the average of y is just 1 over v, the sum of the average of xi, which is v over v, the average of x, and the average of x is 1 times p plus 0 times 1 minus p, which is p. P is the probability of making a mistake using h. So the average of y is p. What is the variance? So the variance, with respect to a constant, the constant goes out as the square of the number. And then because the xi were chosen IID, independent identical distribution, then the sum of xi is just the sum of the variance. The variance of the sum is the sum of the variance. So you get v over v squared, which is 1 over v, the variance. And the variance for a binomial distribution, this is a binomial distribution, is p times 1 minus p. So this is the end game. Okay, so this is the variance. We've seen that in the past. One thing to notice, if v goes to infinity, then this goes to 0. So it will concentrate more and more around the real probability. So the question is how big the validation set should be so that I can, I can trust this Y, the statistic. I can trust the P that I'm getting, by the sampling. So there's different, different inequalities, probability inequalities that you can start using. And there are simple ones and there are better ones that suit our purpose. The most basic one is Markov and Chebyshev, which will not give you a lot here in this case. But what we need to use is the Hofding-Tail inequality, which will give us what we actually want, which is how big the validation set should be. So I just wrote this as an example to show you what breaks here, why Chebyshev doesn't work for us. Should Chebyshev capture the fact that P concentrate, that the statistic concentrates around P, basically capturing the fact that the variance grows smaller and smaller, but it does that in a way that is not very tight. So if you look at Y minus the average here is P, it will be bigger than K times the standard error, which is the square root of the variance. For this to be bigger than K times the standard error, this probability is less than 1 over K squared. So 1 over K squared, if you insert here the standard error, okay, and take K to be 2, then what you get here is something that is not dependent on V, but you get 1 over K squared. But what we really want is 1 over something that is dependent on V, so that we can solve for V and find how big V should be, how big the validation set should be. So the fact that this is not dependent on V, the bound, is not good for us. So instead of that, I'll use the Hofding inequality, which we used previously. And with the Hofding inequality, what we have is that the variable minus the average, for it to be bigger in absolute value, bigger than T, this is less than this, assuming the variable is between 0 and 1, which is the case here. Okay? So each of the xi here needs to be between 0 and 1, then you have this. And we want that to be very small, so we want that to be less than epsilon. Now solving an inequality. This, always in these processes, you get to the point where you could have done it when you were in high school. So this is the point here. After this point, if you understand what you're doing, so you're solving for V, and this is just an inequality that you already knew how to solve when you were in high school, hopefully. So you solve it and you get that V needs to be bigger than this number. What we see here is that the smaller the epsilon, the bigger the V needs to be, basically. Okay, that's what we see here, because it's 2 over epsilon. So the smaller the epsilon, the bigger V needs to be in order for the probability to be less than epsilon, in order for us to trust what we see and take the statistics that we see which is the number of time of success over V, to be a good representation of the real P that we want to get. So this is how you validate, basically this is how you validate the behavior. You validate or approximate the behavior of machine learning model in the field. Any questions or comments on this? Was it clear to everyone?
I follow. It seemed okay to me.
Okay, great.
Eitan, do you think, is there some relation, or maybe can have a relation with the drift ideas that we talked about? Or how does the drift issue affect this validation?
So one of the hidden assumptions here, see, at this stage, is that we can randomly pick up a set of data, a fresh sample of data that represents the way it's going to behave in reality. Okay.
Mm-hmm.
Now, that's where the drifted discussion can come in. Okay, so for instance, maybe you can't really do this. You know, you can't obtain such a sample, and maybe you need some generative model of the way reality will behave in order to generate an approximation of that sample. Okay, so maybe you're able to somehow divide the data into different say parts, we'll call it, or something like that, and you'll have a generative model that can help you generate a good representative data sample. Like usually in things like that, under the hood here, under this very innocent line, lies a lot of assumptions, right? it's not clear that you can obtain such a set.
Yeah.
Okay, and if you know how to obtain such a set, you know a lot of things about the conditions in which the system will be deployed. And that's how it's related to drift.
Yeah. Okay.
Okay. So yeah, thank you very much for joining today, and we'll continue next week.
Yeah. Bye-bye.
Bye-bye.
Thanks.
Thank you, Eitan.
Hey, Tom. Thank you.
Thank you. Bye-bye.